Sasipriya?
Yes, sir.
Yeah. What about the others?
One.
No issue with my voice, right?
No, sir.
So I will ask others to join first one. Can you all hear me?
Yes, sir.
Yes, sir.
Shall we start? Any
Yes,
doubt?
sir.
Any doubt from the previous classes? The design of solar PV system, standalone PV system. Do you have any doubts? So please let me know if you have any trouble with the class. Actually, I'm in a native, so it may be there is an issue with the network. Okay, so I don't know whether it is optimum for our class. So if any disturbance, please let me know. Is my slide is visible?
Visible, sir.
Yeah. Okay, so in the last class, we seen about the design of solar standalone PV system. Okay, so the one of the generally used for home purposes and for lighting purposes of system. So that is what we designed for the previous section. So here we are going to design water pumping system. Okay, so it is one of the important application and well growing applications, and most of the government, okay, so in India or any countries, so they are providing a lot of subsidies to encourage to incorporate their pumping system with the solar. Okay, so if you see anywhere, so most of the government is giving, so about 1 lakh is the cost of for the particular system is, so they will provide at least 20 to 40,000. Okay, so that is the subsidy for farmers to encourage them to install the solar PV system. Okay, so there are n number of systems. Okay, so for pumping purposes and lighting purposes and some other. Okay, so for anything we can use this kind of system. So here we are going to see water pumping system. Okay, so based on different availability of the plant. Okay, so whatever we have land or land. Okay, so with respect to the uh, uh, different plants. Okay, so we can say, so what are the energy from water, water energy required, and how it is can be drawn from the different sources. Okay, so we can say well or borewell or river or something else. Okay, so we can say there are n number of water resources. So from the water resources, so each and every system has different head. Okay, so you can say the water level available is, so from the earth it has something. Okay, so based on the depth, what we have to do is we have to select the optimum motor. Okay, so optimum motor and optimum power solar modules to satisfy the power requirement. Okay, so we know there are n number of pumps and motors are available in the market. Okay, so if you see for any pump, you can say volumetric pump, centrifugal pump, reciprocating pump. Okay, so there are n numbers. Okay, so in generally, so if you see any agriculture or anywhere, okay, so for water pumping purposes, they'll use centrifugal pump or reciprocating pump most of the places, and somewhere they'll use volumetric pumps. Okay, and then motor. So if you go for motor, we have again two categories: one AC motor and two DC motor. So in AC, we have synchronous and asynchronous. Similarly, DC motors, so as a series type or shunt type or separately excited type. So based on the requirement, we can select what type of motor we can choose for the particular application. That is based on our pure requirements. Okay, then power conditioning. So as we seen in the last section, so in the power conditioner, you can say there are inverter, batteries, or controllers, let us say MPPT controllers like that. Okay, so if you want to add or if you want to get the better performance, you can add all the components to get the performance better. Okay, but most of the so because of the cost, so most of the farmers will not be able to buy the particular system. So because of that, what they will do is, so without power conditioner or something, okay, so they will add some only one device, not MPPT or some other systems. So to reduce the cost of the system, they will incorporate some less cost conditioners in between the line to power the pump. Okay, so these are some general. So similarly, the PV generator. So you can say tracking or non-tracking. Okay, so again, so it is based on the thing. So most of the water pumping system, so with respect to the capacity, so it will be very less capacity, not more than 1 kilowatt. So because of that, what happens? So no need to go with the tracking system. Okay, so we can go with the non-tracking system for the solar generator. So it means mounted systems, ground mounted system. Okay, so again, so as I said, there are n number of system and different head is available. So based on the head availability and pump capacity, we can uh, we can drive this much amount of water from the particular pump. Okay, so based on the research, okay, so they have indicated the graph like this. So to choose the which type of pump is useful for us for the particular applications, we can choose based on the this graph. So each and every manufacturers, they will provide you the capping. Okay, so they have n number of pumps. Okay, so they will provide you the rating. Okay, so in any electrical system, we can say the nameplate. In every motor or pump, you can see the nameplate. Okay, so where 1 HP motor or 2 HP motor or 440 voltage or 28 voltage. So similarly, so they will give all the specification in the motor itself. Okay, so you can, for your design purposes, you can take the reading the standard values from the particular pump. Okay, so for a company. Okay, so based on any company, you can choose any company. There are n number of solar-based pumps. Okay, so you can choose solar-based pump are already available pump. So we need to incorporate this means. So what type of pump is installed there? So based on that, we can assume. So what are the things we should consider for the design? Okay, so those kind of things we can estimate. Okay, so based on the following procedure. Let us say first step is we are going to if you want to design any pumping system. Okay, so first we need to know, so what is the requirement of water? What is the requirement of water each day? Okay, so that is why we can say how much amount of water can be pumped from the system, and what is the head available. Okay, so including water head, dynamic head, and your frictional losses. Everything we need to consider in this. Okay, so and then so based on the head and we have the volume. So for this we can calculate the pump rate. Okay, so which means that volume flow rate, and then your based on your sunlight, because we have 6 hours of 6 hours of sunlight, so we can pump only in the 6 hours. So whether we are in need of battery or without battery. Okay, so most of the places there is they are not using batteries. Okay, so when they go for less cost system. Okay, so in that cases we need to consider, so the pump will be operated within the sunlight durations. Okay, so it will be around 4 to 6 hours for our case. Okay, then so based on the requirement. Okay, so this much amount of water and this much we have. So we have both the thing. So from this, so based on the requirement, we can select the pump. So based on the company catalog. Okay, so that I have company's catalog, so which I can share. Okay, so at the end of the class. And calculate the top. Okay, so based on the pump, we want to go with the performance up to the selection of pump and solar system. Okay, so that is enough for us. Okay, so if you want to go for car or pump, so you can calculate based on the formulas. So we know I'll tell you what are the formulas will be used to calculate the pump power and what are the speed of the pump and everything will be discussed. And then so based on all the requirements, we can choose the solar panels. So how much amount of power to be supplied from the solar panel to satisfy the requirement. Okay, so again the same thing is, so I have given you 11 steps. So first step again water requirement. So we know how much amount of water is required and what is the head. Okay, so that is your second step. So type of water sources, so which is nothing but your, it may be a well, it may be a bore well, or it may be a river or something else. Okay, so we need to know what type of water sources. So from the thing we can get how much head is available for pumping. And then water storage, so where it is going to storage. So let us say in the overhead tank, or we are going to place in the small tank in the field, or some we are going to um, water into the plant straight away. So that we have to consider. And then a system layer. So as we know, so if you have all the data, we can do the system layer. So each and every plant. Okay, so we have n number of things. So for if you see for coconut tree, or if you see for banana, so or if you see for guava, so any kind of trees, so which has some particular distance. Okay, so between two plants or between two rows. Okay, so which means that, so because of the developed time. Okay, so what happened? The trees will be hit each other. Okay, so we need to avoid those things. So if you avoid those if you provide the space, optimum space, which provide you the better yield from the particular plant. Okay, so such a way that we need to do the system layer. So which means that, so how your plants will be landed, and where you have to provide your piping systems, and where you have to give the space system or some other things, or everything. You can select it from the layout. Okay, and then insulation. Okay, so we know for the particular insulation, it is not like the solar home system. Okay, so in the particular system, you can do this much. So each and everywhere it is varying. Okay, so if you want to do the better or best performance for the particular system, we can give you the a small analysis. So before you installing the system, so you can go for the site and you can get the data by measuring the insulation data, wind velocity, etc., to optimize the things. Okay, so that is one of the important things. So most of the time, as of now, the solar engineers are doing, so they just assuming the values. So for the particular location, for the particular location, for channel location, so what they will do is, so they will assume the things. Okay, so let us say for Indian condition, so 4.32 is the peak power generation factor. So that is how they will assume small things. So this variation is slight. Okay, so because of that, there is no issues. Okay, if you want to do perfect, you can do the earlier studies and always. Okay, and then step number 6, again, so flow rate, and then head, and then pump selection. So similarly, panel selection, and how you are going to arrange your panel, and then what is your delivery point pressure, and then your, so summary, each and everything you can summarize the thing. So these are the 11 steps. So for complete perfect system, you can do all the 11 steps. Okay, so we can say the uh, for any perfect pumping system. But our case, okay, so based on the as I said, okay, so the most of the things wherever, so the pump, okay, so these are some configurations for the water based system, solar PV water system. So let's say the PVRI is directly connected to your motor pump. So because of that, what happens is, so we can apply. So since your selection is DC motor, we can supply the water. We can supply the current straight away. Okay, so there will be a switch that will disconnect when the load or the overload or any other things. Okay, so it will protect the system. Only the switch is the parameter. Again, if you consider for the second diagram, so there will be a maximum power point tracker. Okay, so based on the maximum power point tracker, we can optimize the power thing. Okay, so that is the second type of system. So apart from this, so if you choose AC motor, okay, you can use these special inverters. So based on the requirement of the motor, so you can choose any type of inverter to provide the AC power. Okay, and then this, that is if you go for want to do install all the things, so charge controller or battery bank with the battery backup, so you can connect like this. Okay, so and then for PVI, so if you want a charge controller, battery bank, inverter, you can provide everything. Okay, so actually if it is inverter here, so mostly your system is AC motor. Okay, so you have to know those things. Okay, so these are some common type of configurations used in the different watering plants. Okay, so for any type, let us say this is the system procedure. To go with step number one, for let us say I'm pumping water from the borewell. Okay, so let us say like this or well. Okay, consider. So these are the water availability. So whatever the available. So from here to here. Okay, so from here to here, you can say there is your total height. Okay, so from the base, okay, so from the water available pump to the top, we can say that is your total height. So based on that, there are different hits. Okay, so one is static water level. So there is no, uh, we can say this is the static. The top level of the thing is static water level, and the where your water is going to run. Okay, that is your draw down level. Okay, so what happens is, if you want to find the static head, okay, that is nothing but your uh, above earth height plus this static head. Okay, so if you add both the values, it will give you the static head and the dynamic head. So all the head, okay, so including A, B, C plus piping. Okay, so if you add the pipe sizes, so pipe height, so that will provide you the total dynamic head. Okay, so we can add plus let us say pipe friction plus pressure head. So everything will comes under dynamic head. So with respect to the given condition, we can choose. So what are the things we can include? Okay, so then the hydraulic energy. Okay, so how much amount of energy can be calculated? So if you have studied your fluid mechanics or basic physics, so you might have come across this formula, rho g qh, rho g qh. Okay, so instead of rho g q, here I used v. Okay, so the volumetric flow or volume required, that is indicated as v. H is indicated as total dynamic head. Capital H is total dynamic head. Rho is density of water. G is acceleration due to gravity. And eta P, that is your pump efficiency, which will provide you the um, total hydraulic energy required by the pump. Okay, so we know for water. So what is the density? What is the value of density for water? So density of water. Thus,
Yes, sir.
yeah. So tell me, Bob, what is the value of density
For water
for
as well.
water? Yeah.
1000 kg per meter cube.
Yeah, so we can say 1000 into 9 point gravity 9.82. Okay, so if you add all the values, okay, so I can say somewhere here. Let us say, so if you divide that 1000, okay, so what we can see is, so we can get that value as, so we can rewrite your same equation as 0.002725 HP. Okay, so this is also a equation that we can use utilize instead of the same formula. Okay, so both are same only. Okay, so, and then so this will be formed by, okay, so for different efficiency levels. Okay, so under for particular heat. Okay, so with respect to if you have the head of 0 to 5 meter, so you can choose centrifugal pump. Or 6 to 20 meter, you can use centrifugal or submersible pumps. And for the remaining, okay, so you can choose. So for the particular head, what type of pump can be utilized. So if you want to calculate the array size, so solar PV array size, okay, so we know the how much amount of energy is required, and we have this much amount of insulation at the particular. Okay, so S is the average daily insulation. So let us say we can say something around 4 or 5 kilowatt hour per meter square per day is the solar insulation at the site. FM, let us say FM is the mismatching factor. Okay, so generally it will be around 0.8. Okay, FT. Okay, so FT is nothing but your temperature or radiating factors. Okay, so if you consider for heat condition, you can say 0.8, or for cool condition you can say 0.9. So if you substitute those things, you will get how much, what is the size of your PV. Okay, so that you can get it from this equation. Or there are three different approaches that I have to show you in this class. Okay, so for design of pump. So from the input to output or output to input, so are in between. Okay, so based on that, let us say, so try to please let me know. Just okay, so you can get answer. You can okay, so if you get issues, you can tell me. So let me design photovoltaic power system, which is operated for 5 hours and to the development of rural irrigation system. Okay, so the capacity of the particular system 25,000 liters per day, and water is available in the 16-meter depth basin. Okay, so we know we have the and we have the volume. Okay, so 25,000 liters per day, and we have the time period. Okay, so how much how many hours the pump will be operated for the rural irrigation. Okay, so if you see for step number one, as I said, so we need to calculate the water factor. Okay, so how much amount of water is it? So that is given in the problem. So we don't have any issues. So 25,000 liters per day is the problem number one. Okay, so on step number two, okay, so we calculate the total okay, so that is nothing but your total head plus frictional losses. Okay, so we can say vertical lift plus frictional losses. So vertical lift they have given us 16 meter. Okay, so 16 meter is the total depth. Okay, so plus and you can add the frictional losses, which means that this frictional losses can be considered as 0.5% of the total vertical lift. Okay, so this is a common assumption. So you can say 0.5% is lost because of the friction. So we know that the total distance is 16 meters. So 16 into 0.005, which gives you 0.008. So which means that you can say your TDH is 16.008 meter. Okay, and similarly your third case. Okay, if you go for hydraulic energy. Okay, so we know the value of TDH and volume. So from this we can say you can calculate your hydraulic energy. That is nothing but rho g QH. Okay, so we know we have mass and G and TDH. Okay, density into volume your mass. Okay, so density is we know water value, and volume we have, let us say 25,000 liters per day. Per hour it will take 5,000 liters per day, which means that 5 meter cube per day. Okay, so 5 meter cube per hour. It is not per day. So 5 meter cube per hour. Okay, so 9.81 and TDS value is 16.00. If you calculate it, so you will get the value of 785.19 joules. If you want to calculate, convert this into watt, you can divide this by, yeah, 36. To get the conversion of joule. Any doubts? Okay, so based on the thing, so I have the power requirement, and I have the lift, how, and I have the volume. So based on that, I'm going to select CRI pumps. Okay, so G4 S Pro 500 series. Okay, so I'll share you the catalog. Okay, so you can get so from the catalog you can select any type of pump for your particular thing. Okay, so let us say so for the given for the selected pump. Okay, so they have given the information that we can utilize the pump for up to 30 meter, and selected DC pump will provide 6 meter cube per hour, and the supplied voltage is 12 volt DC. Power capacity of the pump is 500 watts, and the no load current is 3 amps, and loading current is 10.4 amps. Okay, so what we can do from this is, so from the so we can say, so which is 25 liters per day, which means that 5 meter cube per hour. Okay, so our volume whatever we selected is more than that, so which means that which will satisfy the requirement. And similarly this voltage, so this should be compensated by the photovoltaic system. And 500 watt. Okay, so our requirement is 218. Okay, so 218. So considering the all the gases, I have selected the maximum capacity of 500 watts. Okay, you can select even less than this. Okay, so we can say how we can provide the lesser power system in the next problem. Okay, and then no, these are some current conditions. So based on the different formulas and analysis. Okay, so if you do, so we need to calculate the electricity demand. Okay, so for the pump. So as we see, there is DC pump. Okay, so for pump we have a load of 500 watt, and it is going to operate it for 5 hours. And weekly, I'll operate. Let us consider. So I'll operate this pump weekly 4 days. Okay, which means that we can multiply all the 500 into 5 into 4, which will divide by 7, which will provide you the daily load. Okay, so water rating required. Okay, so which we can calculate. So that is 1428.57. That is your daily load requirement. And let us say we have selected 12 volt. So this is not 48. So just consider. So this is 12. I will change and send it to you. Okay, this is not 12. 48. It is 12. So if you divide both the value, you will get 119.04. So which means that this much AMR per day is required. So we can say 120 AMR per day. Okay. So and if you see for anything, so it is approximately 10.4 amps. So we can say approximately 11 amps. Okay. And if you want to calculate for a year annual how much amount of energy is required for the pump, we can say we have total daily load. Okay, so total daily load 1428.57 into week. So we have 38 weeks per year. Let us say we consider 38 weeks per year, and 7 days. Okay, so which will provide you the kilowatt hour. So that is 379.99 kilowatt hour. So that is your annual energy requirement for the pump operation. Shall I go to the next one?
Yes,
Okay.
sir.
Yeah. So step 5. So this is as usual. So from the previous section. Okay. So after the for step number 4, we have to select the battery. So since the battery, let us say for the system is 12, so I'll consider 12. If you want to run with the battery system, you can design for battery. Otherwise, no need to design for the battery. So here it is 12 volt. So 10.4 amps is the load for 5 hours time. So we can select the battery 12 volt. So whatever the energy generated from the battery, so that is not going to utilize for storage purposes. Let us say we are going to operate only for us, so which means that no need of autonomies. Okay, if you want to give the number of autonomies, you can provide. So there is not a problem. Okay, so here for reducing the cost, I have provided zero no days of autonomy. And the lead acid battery. Okay, so we can say the cup for discharge is 20% battery selected here, and battery efficiency is 80%. If you provide with the previous formulas, we can say so 62.5 AMR battery is required for the particular thing. So we can say we can select 12 volt 1100 AMR rating of battery, so that will satisfy your system requirement. And similarly PV module. So we have so for a pump capacity we need we need 500 watt of energy, and the energy consumption in 1 day. Okay, so we can say daily it will operate for 6 hours. Let us say 6 hours. So which means that actually this is 5 hours. not 6 hours. Okay, so here it is 2500 watt hour per day. Okay, so and provided with the extra capacity, 30% of extra capacity, you can say. So the daily energy required is 3900 watt hour per day. Okay, so based on this, okay, so we have the panel generation factor again. Okay, so we know the panel generation factor is 4.32 for the Indian condition. So we can say total water. So hope your all search it that panel generation factor in the website. Okay, so just try to find how the panel generation factor is calculated. This is nothing but, so based on the all the losses, you can say different derating factors, all the consideration of all the derating factors and the efficiency of the solar module. We can say for a particular solar module it will yield this much. Okay, that is what your panel generation factor. So try to find the formula, or we can see it in the next unit. Okay, so the same formula will be how the solar generation factor is calculated. That I can give you in the next unit. Okay, so and if you substitute all the values, you can get from the solar array capacity. That is, here the capacity is 9.277 watt peak is your total watt capacity of the solar system. And let us say I'll select 300 watt peak solar panel. Okay, so from that we can say, so if you divide by 300, it is something around 4.309, not 43.09, 4.309. So approximately we can say 4 panels. Okay, so it is not 4.39, 4.009. So if you do, it will provide you approximately 4 panels. Okay, so and then we have the formulas. So how to connect your system. And if you want to connect your system in series, we know system voltage and module voltage. So just divide both of them. You get how many number of systems will be in series, and divide with the total number of nodes. That will provide you how many number of panels will be available in the parallel. Okay, so and the total power generation capacity, power rating of the solar array is. So if you multiply with the series and parallel system with the rating, power rating of the particular panel, which will provide you 1200 watt system. So to provide 500 watt of energy to the pump, so your system will be selected as your system should have the capacity 1200 with the 30% extra capacity. And then we can say area of single solar panel. Okay, so for area we have the length, width, and thickness. Okay, so we have different dimensions. So from this length and width will provide you the area. Okay, so that from that value I have calculated the area of a particular solar panel for single solar panel. So we know the total area required. So we have number of panels. Okay, so number of panels around we have 4 panels, and if you multiply with 1.9404, it will provide you the total area required for occupied by the solar panel. Okay, so for extra spacing or extra, okay, so if you provide some 15% extra land, which will give you 8.925 meters square, approximately 9 meters square of area should be required to install your solar PV array in the pumping system. Okay, so that is what the full design of your any pumping system. So again, I'll tell you one thing, I'll summarize you the things. So first we need to calculate water required. So how much energy is required, and total dynamic head, and then hydraulic energy required in kilojoule or joule, and convert this into watt divided by 3600 will give you the watt plan. Okay, so from that you can select your pump. So based on the pump, you can calculate your electricity. So for operation of day and week, okay, based on that you can select your daily load, water requirement, and hour requirement. So from that value, you can select how much, what is your battery sizing, and then your PV module sizing, and selected pump. Okay, so based on the solar generation factor. Okay, so from that you can say number of panels, and then series, how many number of panels in series and parallel. Okay, so from that we can say the area, and then how much amount of space is required for install the particular solar system. Any doubts in this? Is there any doubts? So
No,
even
sir.
if you have Yeah, so please try to go through the slide. So each and every step I have provided you very clearly. So if you can make any correction or any doubts. Okay, so at any time you can ask me. So please try to go through the slides. Okay, so and then that is some more case study. So I took a case study to give you the importance of a particular agriculture field. Okay, so that will give you some more idea how what are the things so should consider for any type of solar water pumping system. Okay, so here we need to design a solar PV pumping system, water pumping system. So for irrigation of banana trees. Let us say this plant has 540 plants. Okay, so we need to install 540 banana trees. Okay, so which with the space requirements of between each and plant and rows. Okay, so for each and everywhere we need to provide 1.98 meters between the two banana trees. Okay, so which will give you the let us say we can say here I selected the square area. Okay, so it is just a small assumption based on my studies. Okay, so you can choose. So from there are n number of agri students here. Okay, you know. So what are the optimum sizing for the particular plant? Okay, so from that you can say you can give you the accurate values or accuracy. So how your watering system and how your etc etc. So everything you can design from here. Okay, so I just gave you the overline. So how to do what are the importance. Okay, so and then so far this plant is located at that is a Tamil Nadu Agriculture College, Trichy. Okay, so with the we know the case. Okay, so 10 degree, so 7.755. So I have just made the problem which is made for some other country. I just made the problem for our Tamil Nadu conditions. Okay, so I just took over some changes in the problem. Okay, so maybe few lines are maybe mistake. Okay, so let's say the study area it has some latitude value and longitude value. Let us say the altitude of the particular location from the sea level is 209, so which is not actual case for the Trichy condition. Okay, so the last 209 meter above the sea level, that is not true. Okay, so and then the PV system sizing was made such a way that it was capable of irrigating 0.165 hectare. Okay, so we need to provide this much. We have this much amount of land. Okay, so if you provide 1.98 meter for 540 plant. Okay, so we need to consider whether this 540 plant with the same gap will satisfy the land requirement. Okay, so we need to consider that. And the daily water requirement. Okay, so that is of 9.72 meter cubes per day. Okay, so that is one of the thing. Okay, so maybe I don't know for we can see so how much water requirement. So based on the some other calculations. Okay, so here I can again I can ignore the here the given value daily water requirement. So just ignore this line. Okay, and the available total unit is 26 liter. Okay, and the formulas, whatever the peak water requirement and what are the different conditions. So everything is calculated and the assumptions are given in the problem itself. Let us say your water requirement, peak water requirement can be calculated for each and every month based on the given formula. So that is the function of graph area and P. Okay, so the P is your nothing but your fan evaporation rate. So that is for each and every month. So the sun variations, okay, sunlight variation is different. So because of that, your pan evaporation rate is varies. So we can based on the given data, so we can get the PE value. Okay, so evaporation rate value, and then PC and KC. So PC is pan coefficient, and then KC is crop coefficient. So based on the different thing consideration, we can say PC and KC value, and then WA. So that is wetted area. So for the particular for each and everywhere you can say for any plant. So the wet area. Okay, so that we need some consideration for the particular plant. Let us say here for banana. So it is around 60%. That is assumed for this case. And EU is nothing but your emission uniformity of the trip system. Okay, so we can say so this is considered as point. Okay, so I'm not going very back to the agree side. Okay, so I just assumed the value based on the thing. Okay, so just try to focus. Okay, so here these are the given data set. Okay, so for the crop coefficient constants, they have given. So for initial stage, it need this much amount of crop coefficient. So based on the whatever table, and for each and every state. Okay, so if I consider, so I'll install my if I plant any plants at January. Okay, so it will almost for each and every crops it will yield you the output at let us say at 3 months or 6 months or 1 year. So based on that we can say, so what are the stages. So let us say at initial or development, middle or late or harvest. So based on that we can say, so what are the coefficient of these values. Okay, so and then the second thing. So for each and every month, so with respect to the solar radiation data, so they have calculated the value of evaporation rate. Okay, so how much amount of water will be evaporated within a day. For January, it will be around 4.09. If you see for May, so that is 13.01. So that the July is nothing but July value is 13 or 3.9. I think 3.996. Okay, so you can see it in the cloud. And then month wise again for the particular location, if you go through the site, so you can get the solar average radiation value as this. Okay, so these are the given data. Okay, so if you provide this kind of problems in the exam or anyone, if you find any type of things, you have to consider, so what is the water requirement. We need to calculate the water requirement, so based on the solar radiation. This is the peak value or average value of the January month or February month. Okay, so for 633.18, okay, so this much amount of solar radiation is available, and how much water, how much amount of water is needed for the evaporation rate of 4.0 for the January month. Okay, let us say for it may be initial stage or it may be development or middle late harvest. Okay, so based on the different conditions, this value varies. Okay, so let us say there are n number of probabilities. Okay, so based on the assumptions, okay, so which I have made, I have calculated all these values based on the each and every month. Okay, so with the various assumptions, you can assume your own values. Okay, so no need to follow the same values for your calculations. Okay, so here your water requirements can be calculated. As from the statement, the crop 1.98 into 1.98 gives you the crop area. So that is the spacing between the plant and P. So for January month, so it is around 4.09. Okay, so then PC, KC, and WE, every value is assumed from the given data, and EU is they are given as considered. They ask us to calculate at 0.9. So from this we can say, so how much amount of water is required for January month. It is the average water requirement for the January. Okay, so for in such a way you can calculate for each and every month. Okay, so from that we can say, so which month the water requirement is more. Okay, so and we have this much amount of average solar radiation. Okay, so if you find the values, if you find the values among all other values, you can say the maximum ratio. So water requirement with respect to the solar radiation is, so at May you can say this is very high. Okay, 0.0253 is high among all other months. So because of that, I'm selecting the peak requirement of the water as 17.22. So because we need to select, we need to design any system with respect to the peak requirement. So here the peak requirement is 17.22. So if you consider some more thing, so let us say I'll assume that as 18 LPD, 18 LPD for the maximum requirement of water for the particular plant in May. Okay, so we can say that is the maximum. So for other months we can know. So this will easily satisfy the requirement. Okay, so that is a concept. Okay, so for the given problem, so I have selected 18 liters per day and even 17.22 as the maximum water requirement for the plant. Okay, so as we know, for if you want to select the solar system, okay, so as we know, the number of plant is 540 and peak water requirement is 18 liters per day, and the total head which is 26. So from the problem statement, so we can say from the water requirement, okay, so volume of water required will be your total plant. So for single plant they are given 18 liters per day, so which means that for 540 plants, so that will be around 9720 liters, so which is nothing but 9.720 meter cube. Okay, so as I said, so if you want to calculate your joule to kilowatt, so you can divide it by 3600 into 1000 by 3600 will yield you the value of 0.002725 into HV. You know the value of head and then you know the value of V. Okay, again you can consider frictional head also. Okay, so I just consider the total head as 26. You can include frictional head also here. Okay, so from that we can say what is the energy required for complete per day. Okay, so that is 688.66 watt hour per day. Let us say for Trichy condition we can say 8 hours in a day we can operate the solar panel. Okay, so which means that you can reduce this time also. So that is based on your assumption. Okay, I was assuming it was 8. So from this we can say what is the wattage, okay, of a PV panel is included. So total 68866 divided by 8 will be 86.08 watt of solar energy is required from the solar PV panel. Okay, let us say this is the selected things for the solar PV module. Okay, so here the watt peak is 74. If you divide by the values, you will get number of panels and extra all the values. Let us say system it has an efficiency of 0.15. Okay, and it has a mismatch factor of 0.85. So if you provide, so we can say if you with the all the consideration, we can say the PV total wattage requirement is 675 watt and selected is 74 watt. So if you divide this value here, you will get 10 number of energies required to give you the requirement. Okay, so and then with the same formula, we can get how many numbers in series and how many numbers in parallel and total one. Okay, so under the area requirement so each and every one. Okay, that is the concept of it. Okay, so try to go through the things. So here I made a lot of assumptions within the thing. So for each and every month the value varies. So in your problem, okay, so if the same problem is asked in your examinations, so will be maybe your questions up to the requirement of maximum water required or up to the solar PV module selection, not to the battery or charge controller or etc. So with respect to the time constraint, we may get the okay. So on the things. Okay. We can see all kind of so the second one is like this. Let us say if you see for third part, so for only okay, so here there are 250 things are available and the number of cattle. Okay, so there is 50 here for human. So which is the for person he need 100 liters per day, and for cattle it needs 40 liters per day. And let us say for monthly average solar installation at the particular rate is 5.5 for each they have provided for every month. You can take the average value. And ambient temperature at pumping site, that is one. And the 5 frictional losses is 1 meter, they are given the value. And static heat, 30 meter, drawn down level, that is 5 meter. So you can add all those values to get the dynamic. And water source is dug well. Okay, with the sufficient yield. So they have given the another water type of water source. And then coordinate for the particular site. Okay, so from the thing we can say for person and for 50 total amount of water. Okay, so which is 8.2 and the per day. Okay, so there is per day and total dynamic heat. So if you add all the values of heat, you will get the total values. And so this is solar radiation. So here, one from May October to December, we will get 5.5. For June, September, we will get 4.5. So you can design minimum for okay, so with respect to the day rating factors, temperature rating factors are mismatch factors, if you consider all the values. Okay, so we can get so divided by 4.5 and we will get this much amount of the water requirement is okay required for the particular system. And if you here this ground force supply system. Okay, so you can, I can share the PPT with the where you can find the graph. Okay, so like we seen in the first one. Okay, so for this for this kind of graph will be provided for the uh, ground force pump. Okay, so they will provided you the so from the graph, they I have made all the values. Okay, so once I give you the graph, you can understand so how the values are taken from the graph. Okay, so and these are the values. So let us say 400 meters of our requirements we can do, and let us say domestic water supply system is 40 meter and discharge rate of 5.8 meter cube per hour at 400 watt peak PV coverage required from the system. So that is what we selected pump categories. And we know the head selectors, that is, and the discharge rate for the pump is and the pump that is 400. So based on the recheck, you can say from the catalog we can select the values. Okay, so from the catalog as well as the graph, by comparison, you can get whether the selected model will be satisfies us. Okay, so here the requirement is something around 400 watt. Here it is 350. Okay, so whatever we selected, so that is more than the so that your system will satisfy. So 350 watt, 750, so you can say for the characteristics. So from that you can say number of numbers. And similarly, we can calculate how many numbers in series and how many numbers in parallel, and and then the total for each what capacity can be each and every module. Okay, and then module cases. First, we select each and every sort of what we can this one and the voltage is 60. And that we can say, so one part is the total supply in that design is satisfied. If you want to check the reliability of the design, you can get it from hydraulic energy. Hydraulic energy. You can, do the hydraulic energy to calculate the hydraulic energy. This number that is the so which means that the selected value is satisfied. So most of the time, your third type of problem. Okay, so you will not get available some extra values. So because of that, you know this any design in the future, it may be used in the future. Okay. So that's it about unit number 2. So we can say unit number 2. Okay, so what we have seen is so the components available in the standalone system or TV system. So for both in general, we battery inverter and PV module and types of PV module and the efficiencies and then what type of system how to particular components, and then we have included each and everything with the application. The standard system for cooking, then lighting, so this can so you can ask me any doubt at any time. Okay, so for unit number 3, almost we have discussed all the components. No need to discuss number 3. Okay, straight away we will see some extra component details and we can okay, so we can complete your unit almost within a week. Okay, so maybe next week we can complete that. Okay. So I'm actually need to take not today. So we'll start with the remaining classes.
Sir,
Yeah.
வாய்ஸ் பிரேக் ஆகுது சார், எதுவும் கேட்கல.
இப்போ ஸ்டார்டிங்ல இருந்தே கேட்கலையா இப்போ தான் கேட்கலையா?
இல்லை சார், இப்போ ஒரு 2 minutes தான்.
ஓகே, நீங்க என்ன பண்ணுங்க அப்படின்னா ஏதாவது டவுட் இருந்தாலோ இல்லை ஏதாவது இருந்தது அப்படின்னா யூ கேன் ஆஸ்க் மீ. ஸோ நெக்ஸ்ட் 2 கிளாஸ் வந்து பார்த்தீங்கன்னா வினோத் சார் இருப்பாரு. ஓகே, ஸோ நான் எனக்கு சித்தார்த்த வந்து பார்த்தீங்கன்னா நான் இருப்பேன் அப்படின்னு சொல்லியிருந்தேன். ஆக்சுவலாக எனக்கு வேற ஒரு ஒர்க் இருக்கிறதுனால நான் வந்து பார்த்தீங்கன்னா அது பண்ணல. நெக்ஸ்ட் வீக் வந்து பார்த்தீங்கன்னா யூ கேன் compensate the classes.
ஓகே சார்.
ஓகேவா? ஸோ we can wind up the session. So if you don't have any issues or doubts, shall we?
Sure.
Yeah, thank you all.
Thank you.